We can get started. Welcome everybody. We were in the other room and someone told us that was not the right room for us to present. So I hope this is the right room for us to present. If you came to see some other talk, stay seated because we're going to tell you about our talk anyway. So we're going to talk about top 5 mistakes when writing Spark applications. A lot of people ask for slides. So the link to the slides is on the first slide, and that's at the right at the very bottom. It's tiny.cloudera.com/Spark mistakes. It's easy to remember, so I'm going to move on after saying it one more time, tiny.cloudera.com/Spark-mistakes. I am Mark Grover, and with me is Ted Malaska. Ted is a Principal Solutions Architect at Cloudera, and I am a software engineer on Spark at Cloudera. Okay, moving on. Something really quick, we also co-authored a book on Hadoop application architectures with some other wonderful co-authors, so there are 4 of us in total. And that's the title of the book and a GitHub link. And Ted is taking a selfie, so everyone say hello. Okay, we wanted to talk about mistakes people make. But really, these are mistakes we made, and we wanted to look smarter, so we talk about mistakes people make. So, first mistake.
Sorry.
That was funny. First mistake, you've got 6 nodes, you've got 16 cores, 64 gigs of RAM. But you don't really know how to size your executors. So you ask yourself, how many executors should I have? How many cores should I have? I have to make sure I don't fall. How much memory do I give to these executors, right? And all these properties exist. So the first problem that people have when they write Spark applications is how do I set all these properties, right? A quick recap of the architecture. You've got a driver program that has a Spark context. You may be using a cluster manager. This could be Yarn or Mesos, or it could be your standalone cluster manager. And then you have these worker nodes that house 1 or more executors, and the executors run tasks. So the first answer that you may come up with is, why don't I make all the executors very granular? So have a smallest sized executor, and you have 1 core in each executor. Remember, you had 16 cores in each node. You had 6 nodes. That makes 96 cores in total. That means you will have 96 executors. Because you had 64 gigs of RAM in each executor divided by 16, which was the number of executors on that node, that's 4 gigs of RAM per executor. This kind of sort of makes sense so far? Yeah? Okay. So that's the answer, but it's the wrong answer. Why? Because you aren't able to make use of the benefits of running multiple tasks in the same JVM. We're using the same JVM for multiple things. So the second answer is, why don't I make them the least granular? I'll make as big executors as possible on 1 node. That would lead to 6-node cluster. That means 6 executors in total. Each executor gets all the memory on that node, which is 64 gigs, and it gets all the cores. I wouldn't be giving this answer if it was right. So this is wrong as well. Why? Because you need to leave some overhead for Hadoop and other OS daemons that are running on a node. So the answer 3 with overhead becomes 6 executors, 63 gigs of memory, and 15 cores. So I've left 1 core for some daemons and 1 gig of memory for some other stuff. Turns out this is still wrong. So you ask, okay, Mark, stop mucking around with us. What is the right answer? And before we get to that answer, here's a graph of Spark on Yarn memory usage. So what I talk about from here on applies to Yarn. Something similar will apply to Mesos. I don't really use standalone, so I don't really know what applies there. But for Yarn, executor memory controls the heap size, but you need to leave some overhead for off-heap memory, things like direct buffers. And that overhead by default is that bottom figure, which is the default is maximum of 384 megs or 0.07 times Spark executor memory. And so leaving that, so here I talk about, so we have to keep in mind that we have to leave some off-heap memory overhead when we size our executors. Other thing we have to keep in mind is Yarn application master also needs 1 core. So Yarn applications for Spark can run in 2 different modes. The first one is client mode, which is what this diagram is showing. In the client mode, the Spark driver is running on the client app, which is the top left corner. And in the cluster mode, the Spark driver is running inside the application master, which is this top middle part. And in either case, you run an application master, which is this blue thing in the top middle part, which runs inside a Yarn container. So you need an extra core for that application master in the cluster. Mind you, that extra core is required for the application master as a whole in the cluster, not on every single node. Also, When we were sizing these brig executors, we were putting 15 cores on each executors. 15 cores per executor leads to really bad HDFS throughput. So it's best to keep the number of executors to something smaller, like 4 to 6 executors, 4 to 6 cores per executor. So with all this new information that we have gathered, we've talked about direct memory buffers, we've talked about how the application master needs a core, and we've talked about the HDFS throughput is maximized when you have 4 to 6 cores per executor. Here's the calculation we come to. We'll start from bottom up. We need only 5 cores per executor for maximum throughput. Our cluster in total has 6 times 15. Why 15? Because 1 core was set aside. So there's 90 cores in total. And then 90 cores divided by 5 cores per executor leads us to 18 executors in total. These 18 executors are spread across 6 nodes. We keep 1 executor at a side for the Yarn application master. That leaves us to 17 executors that will run the real Spark application. Each node gets 3 executors. And then one of these 3 executors on one of the nodes, one of them will run the application master. Once each node has 3 executors, you had 63 gigs of memory. You divide that by 3, you had 21 gigs. But remember, there's some Yarn overhead for off-heap memory. So you subtract 7% from that, you get about 19 gigs. Okay, so the correct answer is 17 executors, 19 gigs of memory for each executor, and each executor gets 5 cores each. This is not etched in stone, right? You may wish to oversubscribe your cluster. If your cluster is not, if your processes are not CPU bound, you may also increase or decrease the number of executors, the number of cores in your executor for different HDFS throughput based on what kind of HDFS interface you're using. But this is more or less the ballpark of where you will land. If you want to read more on that topic, there's a blog post that's really nice on Cloudera blog that you can read about it. Okay, so I'm going to move on to the next tip. Mistake number 2. You run your Spark application and you see this magical piece of text. Size exceeds integer max value, right? And you're like, I don't know what that comes from. And it turns out, if you notice the stack trace, it's not from your application. It's some code in internal Spark, and you try to guess where it's coming from. So why it's happening is that in Spark, you can't have a shuffle block that's larger than 2 gigs. And you ask, what's a shuffle block? So in MapReduce terminology, I know Spark and MapReduce are not the same, but it's easy to explain in MapReduce terminology, so I'm going to use that. In MapReduce terminology, when you have a mapper that does something, it writes data to local disk, and the data gets shuffled around, and a copy gets written to a reducer. This is called reducer local copy, which then reads and then runs a reduce process on it. So the file on local disk that the reducers read is essentially an equivalent of a shuffle block. In other words, this is a diagram. So if you had some mapping happening and some reducing happening in stage 2, there's a shuffle between stage 1 and stage 2. These yellow arrows is essentially the transmission of a shuffle block from one executor to another. By the way, the terminology map and reduced doesn't really apply to Spark. These are all executors, but I use that for sake of argument and explanation. Okay, so remind you again, no shuffle block can be greater than 2 gigs. So you say, okay, well that's dumb. This is big data stuff. Yeah, no. So Spark uses this thing called byte buffer as an abstraction for storing blocks. And a byte buffer is limited by integer's max value, which maps to 2 gigs. So I will remind you one more time. No Spark shuffle block can be greater than 2 gigs. So what does that mean? To put that in perspective, if you are simply doing an aggregation like a group by and there's no, or if you're doing a join in which there's a shuffle involved, then yes, this limit applies to you. If you're doing caching, then this limit applies to you anytime you're leveraging memory. But if you're doing a simple count, then that's okay. If you're reading a simple file from HDFS and printing out the contents on screen, that's totally fine. This limit doesn't apply. It's only when you're doing a shuffle that this limit applies. Okay, this is especially problematic for Spark SQL because the default number of partitions during shuffle is set to 200. Having this low number of partitions leads to a high shuffle block size, which sometimes exceeds the 2 gig shuffle block limit. So you ask, what can I do? The first thing you can do is increase the number of partitions, thereby reducing the average partition size, right? But sometimes your data has skew, and Ted's going to talk about Well, I'm not going to steal his thunder. So we will talk about Skew later, but I'm not a very good movie critic. Okay, so how exactly do you increase the Spark SQL number for partitions? That's this property, Spark SQL shuffle partitions. Like I said before, it's set to 200. And in regular applications, you can repartition or coalesce, and you can supply the number of partitions you want right there. You may also ask what's a good number for a partition size. And the average we have found canonically to be around 128 megs. There's one more thing to consider. Spark uses a different data structure for bookkeeping on the DAG scheduler when the number of partitions is less than 2,000 versus when it's more than 2,000. That means your memory footprint is going to be different based on this magical number of 2,000. And you don't believe me, don't you? So here's the code. In mapstatus.scala, there's a number 2,000 hard-coded here. If the uncompressed size length is greater than 2,000, you use this highly compressed map status. Otherwise, you use this compressed map status. And they have different memory footprint. One of them is, of course, highly compressed, and the other one is not. OK, so what am I trying to say? I'm trying to say if your number of partitions is less than 2,000, but very close to it, bump it up to more than 2,000. Because that way, you will have a slightly lower footprint than you would have if it were lower than 2,000. OK, so confused much? Here's a summary. Don't have too big partitions when you're shuffling, because your job may fail due to your 2 gig limit. If you have too few partitions, you're not making enough use of your parallelism, so you want to increase the number of your partitions. The rule of thumb is to have 128 megs of partitions, and if the number of partitions is less than 2,000, then just bump it up to more than 2,000. And now I'm going to pass it on to Ted.
All right, perfect. OK, mistake number 3. OK, now this happens all the time. When I'm at client sites, if I can't make your job run 10 times faster, I really feel defeated. So the next couple of mistakes are going to be related to that. So you have a data set that when you do a map job on, it takes 20 seconds. But when you do any type of join or shuffle operation, it takes like 4 hours, right? So what's wrong? You're probably doing a skew or a Cartesian, OK? So for a brief overview, the two of you who don't know who Skew is, distributed computing essentially offers this magical, I hope this works, offers this magical solution where if you have 6 threads, your job will run 6 times faster. Skew is the enemy of distributed computing, where essentially it says you may have 6 threads, you may have a 1,000-node cluster, but all your work is actually being done on 1 core. And you would not believe that this happens probably 80% of the clients I go to, right? So how do you address this? I only have 30 minutes, so I can't tell you all the solutions, but essentially the easiest ones are this idea of salting, isolated salting, or map join. Now you can't always do a map join, but let's walk through each one of these. Salting is essentially just adding some randomization to your key, right? So here we have a key that is a foo, right? And we're adding a salt to it. And this would be an example of our skewed data set. So in the real world, think about some skewed data sets, like if you're looking at stock volumes, right? I believe like the ticker Apple sells like at 20% of the total stocks that are traded during the day, but there's over 20,000 shares of stock, right? So that's skewed. If you would just distribute by ticker symbol, that means 1 core is now doing 20% of the work of the entire cluster. And so this is an example of the breakdown of our data set that we're going to play with here. And what you can see here is 1 ticker takes up 50% of our data set, the other one's 25, and then we start getting to smaller portions of our overall thing. Now, if we salted, if we just added 2 salts per ticker, so we had Apple 0 and Apple 1, we get that first pie up there, which looks a little bit better. If we salt 8 times, we get the bottom pie. Now we're starting to get more distributed, right? And you can use any level. Yeah, there was supposed to be an example there. Yes, preparedness. So you can see here where if we had multiple salts, we can diffuse any skew problem, right? And we can actually go up to 100 or so salts. The DAG for this would look like such. We would have a map when we're converting it to keys and values before we would take it into our reduce cycle. We would add the salts. Then after the reduce cycle, we're going to have an aggregation for apple 0 and an aggregation for apple 1. And then we have to reduce those answers. Does that make sense? But the difference is now we're only reducing 2 instead of, with 1 core, as opposed to reducing 20% of the entire load. Isolated salt is a little bit different. Let's say that you have a key that makes up 80% of your data. An example, and this happens to so many people, that your join key is null. Has anybody experienced that? Where your join key, one of the values can be null, and that makes up 80% of your data set, and the rest is perfectly non-skewed. But that one null character, oh my God, is screwing up the whole thing. So what you do there is you filter out the null, and you process that differently. You apply a very high level of salting to the null character, but everything else you don't apply the salting to. Okay? And then map joins, you should know map joins. Map joins is essentially you hold the smaller table in memory, and then you just use hash maps to look it up. But I wanted to do the salting first because that's normally a bigger problem, because if you could do a hash join, you would have already done a hash join. I mean, in map join. OK, that's skewing. Oh, man, I'm going too slow. OK, so the next thing is Cartesians. If you haven't done a Cartesian, then you may not know what a Cartesian is. A Cartesian is when, let's say, you have 1 million records and you have 1 million records, and together, what does that even come out to be? That's like 1 trillion or something? It's like a lot, right? It's so your data freaking explodes, right? And it's 3 days after you ran the job and nothing is getting done, and your boss is telling you that your cluster is filling up, or your S3 bill is now enough to mortgage your entire house. So this is a bad situation. People will say, well, I have to do Cartesian joins. And of all the Cartesian joins that I've ever interacted with, I could get rid of most of them. You can get rid of them with nested structures, with windowing applications, or skipping steps. Sometimes people use Cartesians as an intermediate step to get an eventual answer. Instead of going through the Cartesian step, there might be another way to get to your answer. Just for some background, the reason why you may have gone through that Cartesian is because you implemented it in SQL prior in your old database life. And let's be honest, SQL is not the best ETL language. But we can talk about that another day. OK, how are we doing? We're doing OK? OK. Whew. All right. OK, mistake number 4. OK. So let's say you have you ever ran out of memory? Have you ever had DAGs that were more than 20 stages? Does it seem like your driver is doing all the work, right? If you haven't used Spark, or you haven't used it aggressively. So what's going on here? So this is just mainly DAG management mistakes. Now, how many of you have done MapReduce in the past? OK. You guys will probably not have experienced as much of these. It's the same as people who learn Java after they learn C++. But the people who learn Java before they learn C++ do all these stupid things, right? So for the MapReduce people, you probably already know that what I'm going to tell you is common sense. But to the Spark people, the easiness of Spark is hiding the fact that you may be doing dumb things. OK. So the first thing, let's see, did I miss the slide here? OK, the first thing is shuffles. So does everybody know what a shuffle is? You do a shuffle on a join, you do a shuffle on a reduce, you do a shuffle on a partition. Shuffles are freaking evil. Don't do shuffles. If you can avoid a shuffle, avoid a shuffle. Shuffles require lots of CPU, lots of serialization, lots of network. They're inherently evil. If you can remove a shuffle, and there's lots of ways to remove shuffles, you can use complex data types. You can reuse key structures that you would use as the key to shuffle. So if you shuffle on similar keys. But one of the main things I do is when I go into somebody who's been using Spark, Spark is so easy to write out and express their problem in the Spark language, or in SQL. SQL is even worse. that the logic is perfectly correct, but it creates a DAG that is unnecessarily shuffle heavy. And what you have to do is you first have to go through the iteration of just writing the code that it's correct. Then you have to re-examine your DAG, and you have to say, can I remove shuffles? Do I ever join on the same key twice? Do I ever aggregate on the same keys or partial keys twice? And the biggest example I had of this is someone wrote a query to get the table statistics of, and we're going to go, I think I'm going to give you a link to that in a minute, the table statistics for a table with 300 columns. When they wrote this in SQL, it turned out to be 1,500 shuffles. I rewrote it using a complex object, and we were able to do it in a single shuffle, right? So, 2 more minutes for this mistake. Okay, same thing goes for, this is group by versus reduce by key. Anybody use group by key? Okay, good, no one. Okay, two people. Don't do it anymore. So almost anything you can do with group by key, you can do with reduce by key. There's a few things that, you can do everything with reduce by key. And the difference is group by key puts everything into memory, right? So your algorithms may work perfectly great today on your sample set, but then one day, someone sends you a skewed data set where on that key, now that you have a couple million records that join in that key, and all of a sudden your Spark job blows up in production, you get a call at 2 o'clock in the morning, and then you call me because I'm the consultant, and then you make me come and fix it at 3 o'clock in the morning, and nobody's happy, right? So don't use group by key, use reduce by key, because the difference is reduce by key, it only has to keep 2 elements in memory at one time. Now you can store more in memory. You could use collection objects and stuff like that, advanced objects in your reduce by, but then you have more control. You could say, well, I'm going to have a collection object and I'll keep the last 1,000 or even the last 1,000,000 records. Right? But then you can put a control figure in there that says, if I get more than 1,000,000 records when I'm doing a group by key and I get more than 1,000,000 for this key, throw a log message or spill it to disk instead of just blowing up and the entire job fails. Right? I have 1 minute. I can't really talk too much about this, but there's tree reduce and reduce. Don't use reduce, use tree reduce. And the difference is it distributes the reduce across all the partitions and then only sends the answers to the driver. If you do the reduce, that will send all the data back to the driver, and that will make an unhappy driver. I don't have much time to go into complex types. You can go look at my blog post, which is how to do data quality checks using Apache Spark and data frames. And the idea is you're not limited to a tuple. Go use a hash map. Go use a set. Go use an array list. It's OK. You can use complex types, and you can do a lot in a single reduce structure. Are we doing OK?
Yeah, we got 1.5 minutes left.
I got 1.5 minutes. OK. Have you ever seen this? And if you haven't, you're not an advanced Spark user. All right. No such method error. Anybody? Nobody? Nobody? All right, come on. All right. This means that you tried to use a library outside of Spark with Spark, right? And it sucks. You'll be spending like the next 2 days in Maven, and you're like, man, you'll be pulling out your hair and be like, I just want this to send a record to HBase, or I want to use a different version of Guava, or I was at a customer site and I wanted to use protobuf 3 instead of protobuf 2.5. And you'd be like, why is life so difficult? Well, then you'll learn that you can use these 6 lines, and then all your pain goes away. So if you use Maven Shade, and if you're using a different library that has a library conflict with Spark, you can use this thing called this relocate pattern here. And you can see here I was using protobufs, right? And I wanted to use protobuf 3, and Spark uses protobuf 2.5. And what it did is any place that protobuf, Google protobuf was in my code, when it compiled, it actually turned into company my protobuf, so that there was no class loader issues. Does that make sense? Come on, that's pretty badass. All right, so that was the summary, and we actually made it on time.
Yeah. Okay, so if we looked like we were talking really fast, that's probably right, because they only gave us 30 minutes. And out of that, in the end, they came and said, oh, leave 5 minutes for questions. They're like, oh, great. So 5 mistakes in gangsta style. Size up your executors right. Number 2, 2 gig limit on your Spark shuffle blocks. Number 3, Skew and Cartesians are evil, avoid those. Number 4, Learn to manage your DAG, yo. Number 5, do shady stuff. Maven Shade. Don't let ClassPath leaks mess you up. All right, thank you. The slides are up here. I'm Mark Grover. With me is Ted Malaska. Thank you, everybody.
Now I'd like to open it up for questions.
Yes, sir.
Hey, is there anything equivalent to Maven Shade for SBT that you know of? What was it?
Okay.
All right.
So when your presenters have these blank faces, that means they don't know the answer to that question, and someone else in the audience.
I didn't even have a chance to look. Yeah. Everyone.
So
Open
the
source.
answer was
Crowdsourcing.
SBT
Yeah.
SM assembly plugin.
So another principle is when it works, don't change it. For me, Maven works just fine. I know some people love SBT. I got nothing against SBT. I just don't use it that often.
Great talk. So we also use a lot of complex data types, and I've been pretty hesitant to switch over to migrate to data frames because I don't want to lose my hash maps. Have you guys had success doing that, or?
Do you want, so I use data frames whenever I work in very large companies that have really high data management requirements. I use data frames whenever I need to read or write data, right? So everything is in a Hive table for me, okay? Now, if I can do the operation in SQL, I'm going to do SQL. It may not be the fastest, but it's the easiest, right? Later on, I might want to do something custom. Now, if I'm doing ETL or I'm doing something advanced, that's when I'm going to use my special collections. But when I'm just reading from disk or writing to disk, I'm always doing it with data frames because I want to maintain schemas and I want to maintain all that goodness. Does that make sense? Yeah. But that's a preference. That's not a dictation. That's more just how I like to do things.
What was mistake number 6 that didn't make the presentation?
Oh, okay. That's a good question. We actually had a lot. I don't know if we put slides for that.
What was your big one?
We definitely. Okay, you can.
It was probably I think the thing is no. I think if we had like 15 to start with, and you'll see that we had to talk so fast because essentially every mistake we ended up being like 6 mistakes in one. So like memory management was huge, and we really didn't talk too much about memory management. Well, we did, but one of the really nice things about Spark is as opposed to MapReduce, and for those who didn't do MapReduce, you're lucky. But the other ones, you only had maybe a gig or 2 worth of RAM. Now that you have 16 or 20 gigs of RAM, I think what happens is people get this false sense of I can put anything into an executor, and that's true up until a point, right? And what I generally tell people is if you're doing like a hash join or something like that, and you start to get where you're putting more than 1 million records into a hash join, you should start to feel nervous, right? Like, you can totally fit 1 million objects in a hash map in 20 gigs worth of memory. You could possibly even store like 30 million, right? But the point of it is, if it works today, and it got all the way up to 1 million, is it going to get up to 2 million tomorrow? Is it going to get up to 3 million tomorrow? And there's this concept of bounded and unbounded collections. And so with memory management, I like to only put things in my external memory that are bounded or that I have a rough sense of control of how big they're going to get. The danger is if you start doing that with unbounded, where one day the provider sends you data and oops, I sent you 50 million instead of 60, right? Or something like that.
I'm displaying here the outline that Ted and I started working on when we started thinking of this presentation. I promise this was not last night. At the bottom of this list are the 2 things that we wanted to talk about was just debugging your Spark apps and the problems that you get when debugging your Spark apps, and caching versus persistence that we didn't get. Those were mistakes.
Can I do the debugging one?
I don't know if you have time
really quick.
For that,
if you don't debug your Spark, something's wrong. You should use JUnits and debug like crazy.
Yeah. So if you want to hear us again, tell the organizers to invite us back again. But these would be mistakes 6 and 7.
Yeah, so the unit test, I only have like 10 seconds. The unit test, You don't have to test your Spark on a cluster. You don't have to use up resources on your cluster. You don't have to leave your Spark shell open on your cluster. There should be no reason you blow up on a cluster, maybe a little bit of reasons, but there shouldn't be a lot of reasons why you should ever blow up or experiment on your cluster. You can do all of that in unit tests. And when your stuff works on unit tests and is correct on unit tests, then you can move it to your cluster. And if you were on the cloud or something like that, and you're experimenting on the cloud, that's money, right? You should be doing a lot of that work in unit tests. And you can do that in your JDEs, and you can debug through it, and you can step through your code. It's one of the beautiful things about Spark.
All right, that's all the time we have. Thank you so much for coming. I hope you guys have an amazing afternoon.